Within Chapter 3, we have the idea of stoichiometry and using a balanced chemical equation for quantitative information. Stoichiometry is at the end of Chapter 3, and we want to help the students understand how in a reaction they can calculate how much is produced and how much remains. Through the sequence of ideas, stoichiometry, again, is at the end of the chapter. Two different approaches are shared within the book for solving stoichiometry problems: dimensional analysis and using BCA tables. When we look at the degree of difficulty for the different topics within the chapter and the relative importance, stoichiometry gets a big dark bar around it because it's really central and will be used going forward for the rest of the semester. The topics within that, I've deliberately arranged them in terms of degree of difficulty. A question involving how much product is formed where one of the reactants is in excess. That's the easiest stoichiometry problem students have the most success with. More difficult would be one involving a percent yield calculation. Lower scoring than that would be a question where the task is to identify the limiting reactant and how much of it remains after the reaction goes to completion. Most difficult, the lowest scoring, are questions that are aligned with using a BCA table or particle representations, such as this one here. Nitrogen gas and oxygen gas are added to a sealed container. Based on the theoretical yield, what is in the container after the reaction goes to completion? The particular reaction that I used again and again here, N2 plus H2 to give me ammonia, this is a great reaction to use because all the coefficients are different. And understanding the coefficients and the subscripts, that's the key to have success with these stoichiometry problems, and that's where students have a lot of difficulty. Consider this reaction here. This is one of the first ones where we introduce the idea of their symbolism and a particle representation to go along with a reaction. I ask the questions, well, the students this question. Let's say this is initially in a sealed container, and after the reaction goes to completion, this is in a sealed container. The idea of a sealed container, we're not adding or removing particles along the way. How about this particular reaction? Would this be the same reaction as the first one there? Would they have the same balanced equation? When I ask students this, most would say yes, it's the same reaction. But what I found surprising is quite a few of them would say, but you write a different balanced equation for it. Notice what they're doing. They're writing a balanced equation that's describing precisely what is there. They're not considering it to be a description with the coefficients that you could use as proportions what is there. They're using it to describe literally what is there. I think this is pointing to a conceptual difficulty students often have. I like this FET sim to contrast the students' thinking, confront that with how we want them to think about it. So at the top there's a recipe combining meat and cheese to make a sandwich. 2 pieces of bread plus 1 piece of meat plus 1 piece of cheese equals a sandwich. So notice as the amounts change that we have for the reactants, we're never changing the recipe. We're keeping the recipe the same, but we're changing the relative amounts. And with that information, we can decide whether we have parts left over or if they all combine to make a sandwich. So I think this is right on the mark for what the students need to understand what the coefficients communicate. Within that same FET sim, there's an opportunity to explore different chemical reactions. This would be a balanced one where we're combining N2 and H2, put them in a sealed container to form ammonia. After they react completely, sketch what's in the container. This would be a student's work on this particular question. This one right here is actually more difficult than you might imagine. More difficult because students struggle with what the different coefficients mean, especially here where it's being shown with the products. I know that because this is a real classic question from the chemical education community. This is looking at one of the most difficult kinds of stoichiometry questions, one involving particle representations. So take a second look at this question. It's showing us what's initially in the container. There's a balanced chemical equation, and they're asked after the mixture reacts as completely as possible, what would be in the container afterwards? Now, the choices here, this is deliberately chosen. And by that, I mean, consider this question. Select the picture of 3 cats. This would be 3 cats within the choices. This would be someone who knows what a cat is but can't count to 3. This would be someone who can count to 3 but doesn't know what a cat is. And then questions that are wrong in both respects. If someone initially said this was a cat and then learned how to count to 3, they would move up and choose this next. My point being is that in this particular question, each choice represents different features like that. The very first one right here is to group the product into, say, 2SO3, take the coefficient of 2 and combine it with how many sulfur atoms you have. That's what's being shown within this image right here. This next one would be to say 2SO3 molecules. Well, let's just stick those together because after all, that's what the formula seems to be telling me. This would be doing the same, but accounting for the limiting reactant that you have and the fact that you have in excess 2 sulfur atoms remaining. This one right here would be having the correct molecule, the SO3, but not accounting for a limiting reactant. And then finally, this would be correct. How do students answer this question when they enter general chemistry? I've studied this quite a bit, and about 40% of our students would choose this initially. So this, again, was reading 2 SO3s as merging together those SO3 molecules. I've collected quite a bit of data on this from students that are in high school and before and after their chemistry courses. Notice before instruction in a high school setting, the majority of the students would say this S2O3 representation is correct. And the second one would be, second most popular would be S2O6. Afterwards, we see a migration to S2O6. So there might be some change right there, but very few would be correctly identifying the molecule and accounting for the limiting reactant. It's not surprising that a lot of high school students, if they finish their instruction with S2O6, identifying the answer to S2O6, that when they enter our courses in general chemistry, that's where they start out. Many of them, at the end of general chemistry, retain that same view of what's being shown. If they initially said SO3, the correct molecule, notice many of those again retain that, and a smaller portion are able to end up with the correct answer. Being aware of this, we've begun to include this topic within our instruction, and we're finding much greater success. So in this case, we're finding that we're able to have students reach the correct molecule and account for the limiting, really wherever they're starting from. But this only occurs when we include this within our instruction. If we just ask the question without having explored this, help the students understand it, they really struggle with it. Now, besides particle representations, we certainly do calculations involving stoichiometry. And we have an overview of what the strategy is here. So at the top, I show a representative question. This particular one is asking multiple things. It's asking how much product forms, what's the limiting reactant, and how much the reactant remains. If I was using this with an approach like dimensional analysis, I would first take the N2 and figure out how much NH3 I could form. I take the H2, figure out how much NH3 would form. And the amount that I have would be the smaller value. Recognizing that, I could take that amount of H2 to figure out how much N2 is consumed, and then finally subtract that from how much I initially started. This would be my procedure for this if I was applying a dimensional analysis approach. There's quite a few different features to it because the question's asking quite a few different things. If we're to look at that same question using a BCA table, BCA stands for before, change, and after. We could have the initial information listed. One of the reactants is going to be a limiting reactant, and we can just pick one. Let's just select N2 and test that. If my balanced formula tells me, my balanced equation, that for every 1 mole of N2, 3 moles of H2 react. That's what the coefficients tell me. So a simple proportion would say that if I have 3 moles of N2, it would take 9 moles of H2. I'd pause at that point and say, I can't do that. I can't use up 9 moles of H2 if I only started with 6. So I chose incorrectly for what the limiting reactant would be. So now I can just choose the other one. I began with 6 moles of H2, use them all up. That will tell me that I use up 2 moles of N2. I'm putting minus signs there to indicate that those reactants are going down in quantity. And I can figure out how much of the product that's formed. All of these are simple proportions that I have that are consistent with the coefficients in the balanced equation. And then working down both columns, all of the different columns, I can figure out how much I have for the different reactants and the product that's formed. Notice how the proportions in the change line are consistent with the proportions in the balanced chemical equation when I'm using the coefficients. 1 to 3 to 2 is the same as 2 to 6 to 4. And they have to be because the change line is consistent with those coefficients. That's what the coefficients are communicating. Oftentimes students will say, well, I just don't really see that feature. When they say, I don't see that feature, it really comes back to they are not understanding what the coefficients in the balanced equation communicate. Some questions are set up where a BCA table and the way that it organizes the information, it's a real strength, I think. So consider this one right here. Same equation we've been looking at, same reaction. And it says some N2 and H2 are added to a sealed container. At a later point in time, all the H2 is gone, 4 moles of NH3 are present, along with 2 moles of N2. How much of the reactants were initially added? Given a scenario like this, a BCA table is a helpful way to organize the different details. The N2 and H2 are added to a sealed container, so that tells me I didn't have any NH3 initially present. After the reaction, the different amounts are listed. If I began with 0 moles of NH3, and I finished with 4, it went up by 4. Soon as I have one value in the change line, I can use the coefficients to get the other values in the change line and work backwards to figure out what I began with. This particular setup, to me, really works much better when I'm using a BCA table to keep track of the different parts. Sometimes students ask, are there questions where we're required to use a particular approach? Certainly not, but I feel by asking a question like this, we're really testing their ability to use a BCA table. So the instructional implications are what I've talked about. We have different types of stoichiometry questions in a progression of difficulty from easiest to most difficult. We want to use that information when we're giving students feedback, figure out what they can do, where they are on the progression, and helping them practice to move upward in terms of degree of difficulty. Success for all of these begins with understanding what the balanced chemical equation communicates. What are the coefficients and what are the subscripts communicating? We want to always attend to the coefficients. The number one error that a student makes is not properly attending to the coefficients, either ignoring them entirely or looking at their inverse. Some questions may be better suited for the BCA table approach. Anytime in my own problem solving when I'm asked to report multiple things, I find a BCA table is most helpful because all the answers will be listed.